Welcome back, everyone. Okay, today we are embarking on what is quite literally the ultimate one-way trip. In this explainer, we're plunging straight into the absolute most mysterious, mind-bending environment in the entire cosmos. I mean, imagine for a second that you've traveled to the very edge of reality as we know it, and you're descending into a black hole. We have spent plenty of time looking at these cosmic titans from the outside, but today we're going inside. We are journeying to the singularity. So get ready, because things are about to get really, really strange.
So let's just dive right into this with the most immediate question you'd probably have if you were falling in. What actually lies beyond that point of no return? If you breach that invisible barrier, what do you hit? Is there a physical wall waiting to crush you? Is it just this vast, dark, empty space? Or are you hurtling toward a realm where the very laws of physics that govern our daily lives just completely break down and stop answering us? That is the exact mystery we're unraveling today.
Put yourself in the spacesuit for a second here. Imagine you've just crossed the event horizon. This is it, the ultimate cosmic boundary. By the time you've even blinked, you're nearly invisible to the outside world. Anyone watching you from afar? They've lost you. And from this moment on, everything you thought you understood about how the universe works begins to violently warp. There's no turning back, and there is absolutely no distress signal you can send that will ever reach home.
Section 1. Past the event horizon, the inevitable journey. So, what are the actual mechanics of this environment? What exactly happens to you once you're trapped inside the event horizon? Well, to understand your predicament, we have to look at Einstein's theory of general relativity. Gravity isn't just some invisible, magnetic-like force pulling you down. Gravity is the curvature of space-time itself. When a massively heavy object, like a collapsed star, concentrates all of its mass into a tiny region, it curves space-time to an incredibly extreme degree. So, inside a black hole, the actual space around you is violently bent. Everything, including light itself, is forced to travel along the severely curved terrain.
And yeah, you can go ahead and forget your standard sci-fi escape fantasies. You might be sitting there thinking, well, I'll just turn my ship around and fire the thrusters at maximum speed. But speed is utterly useless here. The problem isn't just that the gravity is really strong, it's that the fundamental structure of space-time has altered dramatically. The geometry of space has quite literally folded in on itself in such a way that every single available path, no matter which direction you point your ship, simply curves right back inward.
Now, this is the crucial point, and I kind of want to slow down here for a second because this is a massive philosophical and physical mind-bender. Once you're inside the idealized model of a black hole, moving toward the center, toward the singularity, is no longer just a spatial direction. It literally becomes your future. Think about it like this. Outside in the normal universe, you can't stop time from moving forward, right? You can't avoid tomorrow. Well, inside a black hole, a freely falling observer cannot avoid the singularity. It's as inevitable as the ticking of a clock. The center is no longer just down, the center is tomorrow.
Moving on to Section 2, the fall, observer versus astronaut.
Let's look at how this immense gravity distorts reality, and how that depends entirely on who is actually doing the looking. If I'm a distant observer, safely hanging out outside the black hole, watching you fall, I don't actually see you cross the event horizon. Because of the extreme gravity, the light bouncing off you takes longer and longer to reach me. To me, you appear to slow down to a freeze frame, and the light from you gets increasingly redshifted, just slowly fading away. But for you, the astronaut, your local clock just ticks normally. You don't hit a physical wall. You don't see some glowing neon boundary line. You just cross the horizon in perfectly normal time from your own perspective, totally oblivious to the frozen image of yourself that you just left behind for the rest of the universe.
Section 3. The physical toll. Terrifying spaghettification.
Now, just because your clock is ticking normally definitely doesn't mean your body is having a good time. It's called spaghettification. It sounds kind of like an Italian dinner gone horribly wrong, but here is how it actually plays out. Step 1. As you fall feet first toward the black hole, your feet are physically closer to the center than your head is. Step 2. Because gravity increases so sharply over such a tiny distance, the pull on your feet is significantly stronger than the pull on your head. We call this difference tidal force. And finally, step 3. This extreme force violently stretches your body out vertically while simultaneously squishing you horizontally. Quite literally, you get stretched out into a long, thin noodle of atoms.
But before you totally panic, there's actually a really surprising caveat here. You might actually survive crossing the event horizon if you pick the right black hole. A supermassive black hole, like the one sitting at the centers of our galaxies, is so impossibly large that its event horizon is pushed way out from the center.
Because of this, the tidal forces right at the boundary are actually relatively low. You could literally drift right through the event horizon of a supermassive black hole without instantly turning into a noodle. The real catastrophic stretching danger for those giants lies much deeper inside, just waiting for you in the dark.
Which brings us to Section 4, the singularity, where physics breaks down. So this is our ultimate destination, the core, the exact place where the journey ends and where human understanding just slams into a brick wall. The singularity, according to classical general relativity anyway, is a mathematically derived point right at the center where all the matter of the star that created the black hole has undergone incredibly severe compression. The math tells us that at this one specific spot, the curvature of spacetime doesn't just get steep, it reaches theoretical infinity.
But here's where we really have to stop and ask a massive question. Does a physical point of infinite density actually exist in reality? Like, does the universe truly allow something to be infinitely small and infinitely dense? Or is the math just playing tricks on us?
Well, when it comes to this infinite density, Einstein's beautiful equations, they just fall completely silent. They create this mathematical situation where the curvature becomes singular, meaning it gives us an answer of infinity. And in physics, I can tell you, when your equation outputs infinity, it rarely means you've discovered a magical infinite object. It usually just means your theory is inadequate. It means the tools we're using to measure reality have officially broken down. The classical model basically fails us right at the finish line.
Section 5, the search for new physics. So, if general relativity can't tell us what's actually at the center, what can? Well, to figure out the singularity, we need a brand new set of rules. We need quantum gravity. This is basically the holy grail of modern physics. Right now, we have general relativity to explain really heavy things, like gravity, and we have quantum mechanics to explain incredibly tiny things, like atoms. The problem is, they stubbornly refuse to work together. Because the center of a black hole is both incredibly heavy and incredibly tiny, we desperately need a framework that merges both of these theories into one unified voice. A completed theory of quantum gravity might finally answer our most profound mysteries. Like, down at the core, is space-time still smooth and continuous, or does it become, pixelated and chunky? Does the fundamental structure of space and time completely change into something we don't even have the words for yet? Or maybe a totally new quantum state of matter emerges under all that immense pressure? We just don't know yet, but this is exactly what physicists around the world are racing to discover. The event horizon tells us there's a hard boundary from which we absolutely cannot return. But the singularity? That asks a much bigger question. Just how far do the laws of our universe actually apply? We've stood on the outside, we've crossed the threshold, and we've knocked on the door of the center, only to find that our current science has just gone completely quiet. Perhaps the universe's next great physics isn't out there in the stars, but waiting for us, buried deep inside the dark. I really hope this explainer sparked your curiosity today. Next time, we're going to be tackling exactly how that extreme space-time curvature works. But until then, keep questioning everything.